I want you to find the derivative of f of x. Find the derivative of f of x, the one at the bottom. As you're handing those up.
Yeah.
Okay. Once your homework is passed, you find the derivative of f. The derivative of f. No names. Okay, you can check with the person next to you. And the derivative of f should be.
Should multiply the four.
Easy.
Okay. Everyone got the derivative of f. Agreement with your neighbor. Okay. Now find this antiderivative. Now find this antiderivative. Hopefully somewhat quickly. That's the goal here, that you can just kind of write it down. Look familiar? Okay. What do you notice? Tell me, what do you notice?
It's still f of x, just over 24.
Basically the answer to the problem that you just did, right? Which was a chain rule, right? So now, can you, what if you hadn't done that first derivative? That's the thing. If you hadn't done that first derivative, could you look at that and say, oh, this is basically a plus x to the fourth to the sixth? That's basically what it is, but then there's a little bit of a mess to clean up, right? What's the mess? How do we clean that up? So this is basically, oh, the x cubed, that's essentially the pop out, right? That's essentially the rate of change of the inside that gets popped out in the chain rule. Because why? That's 1 power less than the 4. So I'm just going to do what? A plus x to the fourth to the sixth. And for the 6, I know I need a 1/6. And for the 4, I know I need a 1/4. This is the goal. And then this is all what? All antiderivatives of this, meaning net accumulation starting at any value x equals a. So it would be this thing, what? Minus this whole thing with a plugged in. Or like f of a, right? So then the generic way to do that is the minus f of a, we just say is some constant. So we just add c. That means the minus f of a, or it allows for any possible a to start our net accumulation from. Okay, and then this is actually the problem we did at the end of class last time, where I kind of gave you a little bit more of a structured approach to it. But the goal is what you just did. You see that as, oh, this is the derivative of basically a plus x to the 4 to the 6th. And the key is that it has to follow that pattern. This x cubed has to be the derivative of the interior right there. Did I start recording? I think I did. Yes. Okay. So questions on that kind of review example. So New example. So the first thing we got to know is, what does this notation with the sines and cosines, when you see sine fourth x, how can we rewrite that to really show what that means? How can we rewrite that to really show what that means? Okay, Alec wants, basically you evaluate the sine of x and then raise that to the fourth. Agree? Yeah, that's what that means, right? So this maybe is an easier notation because it really expresses the meaning maybe better than this notation. Okay, so that's just rewriting it. So now what? If we're undoing the chain rule, what do we've always had the product of two things, right? It was like our chain rule derivatives look like this, a product of g prime f times f prime. So does that mean we can't do undoing the chain rule here, or can we still make it work? The question is, can we write that as a product? What product? Cosine x times sine of x to the negative fourth. Now it's looking, so does undoing the chain rule apply? It applies if we have a popped out function that's the derivative of the interior of the other part. Do we have that? So which is what are we going to focus on to undo this? We're going to focus on exhibit A or exhibit B to undo this? B. Go. Do it. So here's what you're going to focus on. Think about, what do we think? Tell me your name. I forgot. Yeah. What is it? Yanni? What was your first attempt at this? What did you think? Okay. So you want sine x to the negative 3. Okay? So that's a good first attempt. Or we could even make this first attempt a little bit. Did you do anything else? Or did you? Yeah, so whenever you do this power rule, you can just throw the negative 1/3 on there. And that could be like our first attempt. But even if you did sine to the negative 3, that could be a valid first attempt too. And then how do we check it? Take the derivative. Okay, so now what's the derivative of that? So the derivative is negative 3 times negative 1/3 times sine to the negative 4 times cosine. Do we have an exact match to what we started with? If we have an exact match, then our first attempt was correct. And we do have an exact match. So, answer? Negative 1/3 sine x to the minus 3. And then we want all possible, don't forget the plus c. On your web work, some of the problems have the plus c outside of the answer box. So they've done it for you. Others don't. So you have to watch for that. And if you don't put the plus c, if it's not there, then it's not right. Because this is called indefinite integral, which means all possible net accumulation functions starting at any value a. So we need to compensate for that minus f of a, right? That minus f of a is just this constant that we add on. Questions on that example? Okay, go. See how this one goes. Give it a shot. Okay, tell me your name again. Yeah, Melissa. Okay. Did you get started on this? No? Not even started? Just one step? But we got to, yeah.
6 times 1
over. Okay, perfect. Check. That's something, right? 6 times?
1 over 2 minus 4.
All right, so if we want to use an exponent, how about an exponent?
So 2 minus 9x to the negative 1.
Okay. Okay, so Melissa got us started here. Good first step. Okay, so we got undoing the chain rule because derivative of a linear function is constant, right? So it doesn't matter what the constant is. We can clean up any constant mess that comes our way. So essentially, we can do undoing the chain rule because the derivative of what's inside here is essentially what's outside here, a constant, okay? Even if it's not the right constant. Okay? So then, who tried the power rule? Who tried the power rule? Yeah, tell me. What happened? That's okay. So you do?
So it would be -6/9 times 2 to the 9x.
So this is 0, and then you need a... All right, so -6/9. But then if you have 0 here, you also need a 1/0. Okay. So, first red flag, 2 minus 9x to the 0 is what? You just lost your function. Okay? Second red flag, 1/0. Only 2 people can divide by 0. My daughter and Chuck Norris. Okay? All right, so, but no one else can. So this doesn't work. My daughter's smart. Okay, so there's red flags going off all over the place. Something's wrong, right? Power rule doesn't work. So we go back here and we say, we just got the derivative and it's something to the -1. And so something's, what, when you take the derivative of it, do you get 1 over or to the -1? Yes, sir?
The natural log.
All right, so this is the one case where you're not going to use the power rule because the derivative of natural log is to the -1. Any other power, any other real number power, but not non-zero and not -1, you're going to use the power rule. But when you have to the -1, you're doing the antiderivative, we need natural log. So, you want to go for it? Tell me.
So, since you have 1 is 2 minus 9x to the -1, since the derivative of the natural log, the derivative of a natural log is 1 over
Okay.
x, you take that, basically you antiderive that into the natural log of 2 minus 9x.
Okay.
And then, since you have a 6 as a constant,
Okay.
you have to multiply it by -2/3 because the derivative of 2 minus 9x equals -9.
Okay.
So multiplying that by -2/3 will get you 6.
All right, so let's just break it up. We're just going to keep the 6, and then what do we need to take care of the -9? -1/9. So that's where he's getting the -2/3, right? The 6 just comes along for the ride, and then we need the -1/9 because we know when we take the derivative, it's going to be the rate of change of the inside, and it's going to give us a -9. A -9 that we don't have over here, right? So that's where he's getting the -2/3. So -2/3 ln of 2 minus 9x plus c. Okay, now there's another issue here. There's another issue here. The other issue is, what is the domain of this rate function? I can get valid rates of change for what values of x? What values of x can give me a valid rate of change? Not 2/9, but anything else, right? Anything else. So negative numbers work?
Yeah, negative.
Positives, negatives, doesn't matter, right? So just as long as x is not 2/9. Why? Because then you get 0 in the denominator. Okay. Again, we're not my daughter. We're not Chuck Norris. So we can't have 2/9 for x. But what about this? What's the domain of this? So now we have accumulation function, and we want it to have the same domain as this rate function, right? We need that accumulation function to have the same domain. What's the domain of natural log? You know what the graph looks like? What's the domain of natural log? So what value? So if I were to graph the natural log function, for what values of x is it valid? Anyone know? Greater, is it greater than 0? Yeah, good. So you should be thinking greater than 0. So that means this argument of natural log has to be greater than 0. Not the same domain as this. So what adjustment to this will make this work for the same domain as that. So if I need that argument to be greater than 0. Yeah, if we have the absolute value of 2 minus 9x, then we get the same domain that we have for the rate of change, right? We still can't have 2/9. Natural log of 2/9 is not valid, just as the rate at 2/9 is not valid. But any other x value gives us a valid rate and then a valid accumulation. So remember in the web work, whenever you have an antiderivative of natural log, don't forget the absolute values. It will count it wrong if you don't have it. Don't forget the absolute values when you do an antiderivative. So again, it's about the domain. You have to have the same domain on your rate function as you do your accumulation function. Is that a question?
I was just going to ask if there are other functions that we do that have domain like restrictions.
I don't think so. I don't think so. Well, maybe. This is the one that comes up the most, right? Because there's lots of times when you have some function to the -1 or just divided by that, and you end up using natural log. So this is the one to watch out for. Right? Nothing else is coming to mind at the moment. Okay, any questions on this? So answer, -2/3 ln absolute value 2 minus 9x plus c. One more. This one's a little trickier. See if you can figure it out. This is trickier. Okay, so first tip is don't write it as 1 plus x squared to the -1. This helps you see it a little better, because you could do that, and then you might think natural log, but does it fit for natural log? If it fits for natural log, then tan inverse x has to be essentially the rate of change of 1 plus x squared. Is it? Not even close, right? Rate of change of 1 plus x squared is 2x. We have tangent inverse x, so it's not natural log of 1 plus x squared. Okay, so instead write it this way, and then my next suggestion would be really try to identify what is what. So here's our pattern, right? Here's our pattern. G prime of f times f prime. That's chain rule. Which is which? Which one is G prime of f? Which one is f prime? That might help kind of solve this puzzle. So talk about it. If you need to talk about it, talk about it. Oh, and wait a sec. Sorry. That -1 is not the power -1. This is arc tangent. So maybe let's write it that way. Don't get messed up that it's not tangent x raised to the -1 power. This is a different function. This is the arc tangent function. So let's do that too. There we go. Maybe that will help too. Okay, which one is f prime? Which one is f prime? Would f prime be arctan, or would f prime be 1 plus 1 over x squared? Yeah, so if you first see that this is really f prime of x, right? This is the rate of change of arctan. So arctan is like f of x, right? But we need that, what, g prime f of x, right? So the question is, what is this g prime function such that arctan is the interior function? What would that be? Arctan x is interior. What's the extra? Anyone got it? Did anyone solve this? Tell me. All right, yeah. So what would the g prime be? What's the external function for this that allowed you to do that? No, that's the derivative of the inside. I'm talking about this. So this right here, the g prime. What are you doing the antiderivative of? Well, you got to the, you said, what's that? But that's the antiderivative. So what is it that you took the antiderivative of? To the first. Here's the key. To the first power. That's your G prime. Now do it. See if you can do it now. Your G prime is something to the first. G prime is something to the first. So see if you can finish now. But you don't need to do that, right? Are you trying to think of that to solve this problem? Or are you just thinking because you want to think as a different thing? Because the question has nothing to do with, right? This is your f prime. So the rate of change of arctan, this is your pop out. This is your pop out, right? For chain rule. So we're going to do the antiderivative of this. No, it's to the first. Interior function stays the same. It's just the antiderivative of something to the first. Power rule. What's the power rule if it's something to the first? To the second. It's so easy, it's hard, right? Arctan x to the second. Power rule. And then we need a 1/2. Let's see. Thank you.
I was trying to think of a trig function.
The internal function stays the same, right? You don't need to know what the antiderivative of arctan is. The interior function stays the same. Here's your f of x. It stays f of x. All you need is the antiderivative of the exterior function. Yeah. Okay, so that's harder to see. Okay. Any questions about that one? We're done, right? So check it. Take the derivative. What's the derivative? 2 times 1/2 times arctan to the first times 1 over 1 plus x squared, the derivative of arctan. So there it is. That's exactly what we started with. Okay. So it's exactly like all the others, but harder because we don't write to the first power normally, but that's what you have to use. Power rule on something to the first power. Okay, so did I lose you? Yeah.
How is the derivative of arctan 1 over 1 plus x?
That's just a rule you learned in 270. So that was one of your So that was one of your derivative mastery rules that you learned. So for the mastery test, you learned all the inverse sine functions, all the trig functions. Yeah, all the rules. So that's just one of the rules. So again, this thing about antiderivatives is just really about knowing your derivatives really well. So we got to remember. And on that note, I have posted. If you look in homework now, the first post in homework is the list of the primary rules. So, no, we got to learn it, right? So the whole point of the mastery test was that you memorize this stuff. That was the whole point of the mastery test was that you memorize this. So, hold on. So use it all you want. Have it right there next to you to do all these antiderivative problems. But then when it comes to the test, you've got to know them because this was prerequisite knowledge from 270. But I got all the trig. I got all the inverse trig, the basic ones, and then your general rules. So right now we're learning what undoing chain rule, which is going to involve all these elementary ones here. Okay, so that's posted. First post right now, list of primary derivative rules in the homework assignment section. Okay, let's do an applied problem here. All right, so a culture bacteria in a dish has an initial population of 250. and then grows at a rate of 50 times e to the 0.3 t cells per day. So I want you to write two expressions for p, which is a function. That p function is the population, so t days. So t days. After the initial measurement. So in the two ways, I want you to write that expression for p, p of t in open form, and p of t in fully simplified closed form. Fully simplified closed form. So take 5 minutes. See if you can do this. So you can do this. And you never ever have to, unless you're taking a quiz, you never ever have to wait for me to tell you that you can talk to each other. Okay? So yeah, take your time to think about it yourself. That's fine. But you're always welcome to. So remember, net change, fundamental theorem. Fundamental theorem. When you have an integral as net change, it's going to be the antiderivative evaluated at x minus the antiderivative evaluated at a. This has nothing to do with the 250. There's nothing to do with the 250 when you apply the fundamental theorem. Lots of you are kind of, I mean, yes, in the simplification you can put things together, but in that first initial step of writing closed form, you're going to apply the fundamental theorem and hold on to the 250 separately. Does that make sense? Back. Zipping, that's a read. Can you read it in the back? Yes. Okay, I think most people did. What I saw, lots of you did really well in the initial step. And so I like putting the 250 on the left so it doesn't find its way maybe into the integral if you're not careful. So I like putting the 250 first. But then also it's kind of, that's what came first anyway, right? It's all the accumulation before the initial measurement. And now we start accumulating at this rate. So time equals 0, okay? And so, so then from here, to get closed form now, we're going to rewrite this using the fundamental theorem, right? That means we need the antiderivative, and we're going to evaluate it at t and 0 to get the net change from 0 to t, right? So your antiderivative is what function gives you this as its derivative? So this is like kind of a pretty easy one, right? If it's e to the something, the antiderivative is e to the something, right? And then you got to think about taking the derivative of that. What happens when you take the derivative of that? You get in the chain rule, you get a 0.3 multiplied. So when we do antiderivative, we need divide by 0.3. Does everyone follow that? So that's the goal, that you can think through that without doing a little u substitution that's going to take twice as long in this case. So we know the antiderivative of e to the something is just e to the something. If we were to take the derivative of that, we'd have a times 0.3 that we don't have there. So we need to divide by 0.3 the antiderivative. So it looks like this. So here's our antiderivative. And here's a notation I haven't mentioned yet, which is really helpful. So what you can do is you can write the antiderivative, which is the 50 divided by 0.3 e to the 0.3u. And then now we have the antiderivative, and this bar means exactly this up here. It means evaluate it at t, evaluate at 0, and subtract. Find the net change, right? Find the net change from 0 to t. That's what this bar over here on the right means. So it's nice because you can break it up into two steps. You can focus on the antiderivative, and then plug in your final and your initial. So when you do that, you get 250 plus the antiderivative at t minus the antiderivative at 0. Any questions so far?
Would you let us put it like that on a test?
What do you
Like the one where you have the line?
Sure. I mean, but if it's asked for the fully simplified form, we have to keep going.
Okay.
But yeah, you can use that. Yes, absolutely, you can use that notation. Yeah, if I'm putting in a PowerPoint, then for sure. Yeah. Okay, and so then we can simplify because that minus 50 over 0.3 e to the point, is that 0? We plugged 0 in. Did we get 0? Watch out. Just because you're plugging 0 in doesn't mean you get 0. There are cases like this one. You plug 0 in, you don't get 0. But that's a common mistake. Okay? So when I plug 0 in, this all is 1. E to the 0 is 1, so then I get minus 50 over 0.3, and I can combine that with the 250. So the final simplified version is this. And I took a decimal approximation because we're talking about an application. So with application problems is when it's appropriate to have a good approximation. You know, when you're in the field, you don't talk in square roots and e to the somethings, right? You talk in just good approximations. Okay, so we got our open form here and our fully simplified closed form here. Any questions on that? Do you follow? So some of you had some, once you got the open form, you did some interesting things after that. So I just want to make sure you follow it. Yeah.
For the final simplification, I understand with 83.3, like what it is, but why is it, like, why did it come from? Like, is that just that's the value of that?
Yeah. So it came. It's partly from the 250, and partly from this value that we need, so that at 0 our net accumulation is 0. So this value is so that at 0 the net accumulation is 0.
So it's 250 minus the f of
Right.
0.
Yeah, exactly. Yeah, it's just combining these two.
All right.
Other questions on getting to the closed form? Do you follow it? Okay. So now, question. I want you to represent the population, represent it 10 days after the initial measurement, and then find the value. So representing the population 10 days after the initial measurement. How many have it? I have it. How many have it? Represent the population 10 days after the initial measurement. Just represent it. Everyone should have it by now. Less than half. Right here. Tell me your name. Yeah. Carmen. What is it? So, but what's the representation? So how do we represent?
So it'd be 166.7. 3 times 10.
Okay. But even shorter and quicker and easier than that. Micah. P of 10. P of 10, right? So when I say represent the population, if you're working in GC, you've defined the function P, and you want to find P of 10, what do? You type P of 10. You type P of 10, right? And it just tells you what it is if you've defined that function. So that, again, function notation. Got to get in the mentality of function notation. It's really helpful. Okay? Find the value. So do you want to use open form, or do you want to use closed form to find the value? Of course, closed, right? And that's the motivation here for all these rules that we're going to learn to find these antiderivatives is closed form is going to be the desired way to go to find it, to do an example like this. What is the population after 10 days? So P of 10 equals?
It's like a negative.
250 plus integral from 0 to 10. Okay. What is it? 166.7? E to the 0.3 times 10. What Carmen said. Easy calculation, right? GC, snap. Graphing handheld calculator, snap, right? Not O snap, but A snap. Anyone got the value? 1,434. And then if you had a decimal, what would you do with it? Round up? So if it's 0.25, then number of bacteria would be 3434. What if it was 3434.85? Still down, because you haven't, at 10 days, technically you haven't gotten to the 35th bacteria yet. It's still, you would truncate. You wouldn't round. You would truncate. So no matter what the decimal is, you would truncate down because you haven't really reached that next bacteria yet. Okay, last question. Represent the change in population from day 8 to day 15 in open form in the simplest way you could in open form. So how can you represent the change in population from day 8 to day 15 in open form in the simplest open form you could? Represent it with function notation and find the change. So 3 tasks. So A, represent in open form, represent with function notation, and find the change. And for open form, the goal is what would the simplest open form we could write be? What would be the most concise way to write that in open form? So think about it. Talk if you need to. Jake? Jake or Jake? Jake. What did you come up with for the open form?
Well, for the function notation one, and then just
Yep. Okay, we can use that would be function notation. That would work. What about open form? Scott?
You could write an open form, just the integral from 8 to 15, r sub p of t, we've already defined it, rt dt.
So we can do this apart. We can do this apart from the p function and just think about maybe a new net accumulation starting from 8, right? We're going to accumulate starting from 8 up to 15 at that rate. And then how are we going to get that value? Yeah, so we're going to use this, right? We're going to plug 15 in here. Or, put the function, your closed form function in GC, and then what are you going to write? Just write that in GC, and it'll tell you the answer, right? Put the closed form function in, p of t equals that. Or open form, but, and then just type p of 15 minus p of 8. So you're going to want to hear this announcement.